בדיקת מיקרופון. שומעים אותי? כך שומעים? בדיקה עומק. כן? פרבוליק כללי. צורת מסך, צורה נסתרת. צורה נסתרת, הבנתי, למה נסתרת? כי אני לא יודע, אני מבין אותה. טוב אחרון.
רגע, רצית להעביר עוד שיעור?
לא, זה את רצית שאני אביא עוד שיעור.
מה?
זה את רצית שאני אביא עוד שיעור, אני סתם הופתעתי מזה שזה נגמר מהר. אני חושב שאני לא רוצה אפשר להתבייג. זהו.
הכיוון שפשוט קריסמוס.
נכון. אבל זה חלק מהפעם.
אמא לא אוהבת.
את מה שאני מנסה לעשות?
לא, סתם, לא בחינות.
הסמסטר הבא שלך לספר כבר יותר טוב.
כן, אני לא יודעת אבל עד כמה. אני אגיד לך אבל איזו עוד בעיה יש לי. אני בטוח צריכה לקחת את טובת החברות הגדולות.
אגב, יראת משהו לגבי הנושא של
ביטלו את זה. כאילו לשנה הזאת.
לשנה.
כן.
זאת אומרת, גם סמסטר הבא.
כן,
מה זה אומר לשנה הזאת? כאילו,
זה אומר שמי שהתחיל השנה, אז הוא לא... כי הם לא הודיעו לנו את זה. לא רשום באתר שלהם.
אבל מהשנה הבאה זה, כן? עכשיו צריכים לשנות את הדרישות מהסמסטר הבא, כבר שלא. עכשיו צריכים לשנות את הדרישות בסמסטר הבא, בקורס שאני מעביר את הסמסטר הבא, אבל נראה שאני כבר רוצה.
אוקיי. כן.
לא שזה כן נכון.
כן, אז הבעיה היא שאם אני רוצה לקחת גם עוד חברות ובאמת גם את התחום של שחר וגם את התחום של פנימה, אז נתן את זה 7 שעות.
7 שעות.
אבל מצד שני אני לא יודעת אם אני באמת רוצה.
אבל זה יהיה מחת. זה יהיה מחת.
כן. עדיין. בעייתי בשבילי. אבל ממש יכול להיות שאני לא יוצא לכם. אבל אני כל הציבור. וממליצים לי על הקורס של רן ובאופן סוגרנה. יש הרבה קורסים.
מה זהו? בגלל מקרה שאני אעשה בגלל מקרה שאני אדבר באנגלית, זה רוצה למס וידאו. טוב?
כן.
זה מה שיש. Okay, so let's try to start. So today is the last lecture, so I will try to go over more material in less details to give you a flavor of where it can go. So first thing, let's go back to the live functors and the live categories. So what we said before, that we have a functor from between two obedient categories, and say it is left exact, so map 1-to-1 map to 1-to-1 map, but not onto map, not necessarily to onto map. Formally, it means that it maps left exact sequence like third. Oh, so even short exact sequence, it maps to f of x, y. Then, but here you can of course put 0, but then it will stop being exact. But this map is onto this number stuff. So, and we want to see how much it's not exact and some way to match it. So we say that sometimes we have sequence of functors, R I of f. So if the functor is left exact, we say we derive it from the right, because measure how much it's not exact from the right. All this theory, of course, can be done in reverse by passing to the opposite fatigue or just saying the words again.
Right, so this is called the derived function.
Yes, but I didn't define what it means. Say that sometimes you have sequence of functors RIF, and they didn't say what they have to satisfy in order to be called derived. I said only one thing, which is kind of the main thing. So of course, they have to be functors, but you also have to have morphism. Like natural morphisms, it depends naturally on the short exact sequence. It depends factorially on the short exact sequence. In any case, you have such short exact sequence. You want morphism from f of z to R1 of R1f of z. And now, since it's a functor, you can also not say face. You can continue to R1 z, R1f of z. And again, out of the structure of being sequence of derived functors, you want a morphism like this. And it depends factorial and the sequence. That's it. So you want all these morphisms and you want this sequence to be exact. Of course, these conditions does not define uniquely the sequence of functors, because even if the functor f is exact, you can just put here some idiotic stuff and declare this morphism to be 0. But so we need additional conditions in order to call it a right now. And here is a possible definition of additional conditions that will define it uniquely, but you don't really have to have them in order to define it uniquely. So
does it have to be
yes, so each of these guys is a functor, and the morphism from here to here is functorial of the short effect. And also other morphisms of this type.
No,
Yeah.
but I mean, you want, if you have a natural transformation from f to an alpha functor t,
Yes.
you want, like, you wanted to induce some natural transformation.
You ask whether the act of deriving a functor is a functor. And eventually, yes, but at this point, I don't even define this act, so I cannot.
But that's what you want.
Yeah, but I can't put it as a condition of what is a derived functor. Because,
okay.
But at the end, yes, eventually it should be like this, but it's a bit problematic to formalize what it actually called. So let's start with some minimal plan. So suppose we are given such a system that we will for now call derived functors of f. We say that an object x in A is f acyclic if R I of f x is equal to 0 for all I.
We say that x is
F acyclic.
f acyclic.
From acyclic with respect to it. I forgot to say, of course, that R 0 of f and negative usually don't exist, but if you want to say just yes.
Okay. Wait,
So if all the positive derived functors are 0, I call the object acyclic. So in real life, I call it acyclic only if all the actual derived functors are 0, but I didn't define what it functor yet, but yet I would call it acyclic for now. And now we suppose we have this additional condition, but for any for any x in A, there exists a map from X to I such that and embedded, not just a map, I think such that I is X.
Okay, I is some other object.
Yes.
It's a more.
Monomorphism. Now, statement, theorem. So I would formulate like this, and then if then R I of F R uniquely defined. Uniquely defined, of course, up to isomorphism. At this point, I will not say up to what this isomorphism is unique, so unique you demand that. So you could define the right functor like this: a sequence of functors such that this axiom satisfied, and such that for any object there exists object I, such that I is f cyclic, meaning that all the functors vanish. And this would be a good definition, except of the fact that it doesn't cover all the cases where we want to say that there are the right functors. So there are cases where we.
Wait, so what you're saying is.
It's like definition one, not final definition of what is the right functor.
So you say that if we look only at RIFs such that they.
So that there exist enough cyclic objects with respect to them, then such this defines reality. If there are such, maybe there are not, but if there are such, sequence factors, then there. But sometimes we will want to say that functor is have the right functors even if this is not satisfied. And for example, one way that you can relax it is to ask that I will not be a cyclic, but the image of RIF of X inside RIF of I will be zero. So you have kilos of problems in X, but maybe add new problems that you don't have. This also, I think, defines it. And you basically can relax it even more. So, for example, if you work in some world when you have elements, so you work in some category that have notion of elements of in the object, then often you can say this is not a formal statement, but that if you know even less that for any I and for any element in RIF of X, you have a morphism that keeps this specific element, then under some additional condition maybe it's also defined in the system. So this is why it's not very good. Definition in general, but it works in many cases. Okay, so one case when it works is when we have enough injective objects. So now let me define what are injective objects. What are injective objects and what are projective. So in general, a cyclic objects are objects that think that F is exact. Why? Because if an object is a cyclic, then you see that any exact sequence that starts with this object goes to exact sequence because this is zero. Yes?
Yes.
So a cyclic object is an object that thinks that the functor is exact. Maybe before this, I want to say, how do you prove this uniqueness? Because the idea is that once you have enough cyclic objects, then you know how to compute the right functors just using these axioms. And the idea is that you start with X, and then you embed it into some object I. This we can pursue. No. And now you can say that computing the right functors on X and computing the right functors on C is kind of very similar task. Why? Because you can write this sequence f of X, f of Y1, f of C1, R1, f X, R to R1, sorry. But this is 0. R1 0. R1 F. R2 X 0.
So R1 of F of T is equal.
Right, exactly. What after you have these two zeros, when you have such short, very short in the sequence, it's just isomorphism. So this isomorphic to this. So if you know all the derived functors of C, you also know all the derived functors of F, except maybe this one. But even this one is not so bad. It's just a co-kernel of F. So if you know,
Yes.
you know it like factorially enough, then okay. So now you want to compute the sorry the co-kernel of this map. So this is just defined by F.
Yes.
Well defined, and all the others you have to do it from C, but also you have a shift. Yes, you need to compute, like if you're interested only in 100 first the right functor of F, then you need 99 the right functor of C.
Yeah.
So I want to say you continue by induction, but to know that the induction over, you need to know, okay, maybe C is as bad as X. But you don't care. Even if C is as bad as X, you improve the situation because you change the index. So you compute new functor. So theoretically, you can compute everything. So this is a very complicated algorithm or inductive algorithm, but it should give you a full computation. But then there is a way to just phrase this algorithm in one large set. And this is based on the notion of acyclic resolution. Again, you need to have enough acyclic options. You have X to I1. And this is how this is last time. Now you have this C. C you can embed into I2. So overall you have a map from I1 to I2. And then you will have C2, which is a co-kernel of this map, which you can, the co-kernel of the map will be C2, which you can embed into I3.
Right, so this is just an acyclic resolution.
This is the way to construct the cyclic resolution. So I didn't define what cyclic resolution means, but this is an extension.
Acyclic, not cyclic.
Acyclic, yes, no cycle. Acyclic because the objects have no cycles, because the idea is that the derived functor is something that compute how much a functor is not exact, which often has to do with something like global that doesn't close well. Yes, if you have you can do a loop, and in each point you don't feel you're doing a loop, but at the end you get nothing the point you start. For example, you want to break the square root, and you see that we can do it locally, but globally something breaks down. And these are the places where you have cohomology come into, like the functors come into it. So you can continue indefinitely, and then you can erase X. And here you just embed. And what you get, so here when you continue indefinitely, you get an exact sequence. Here you get not exact sequence anymore. You can compute its cohomology. You can model the image. So the stupid thing in terminology, when the complexes goes right, then you call it cohomology, and when you go left, you call it homology. And somehow in algebra, at least it's more common to talk about cohomology, better behave from this point of view. I think topology is more common to homology. So we start with this popping out without any intrusion, but this is. And so the first cohomology is X and all the others are 0. And complex which satisfies this thing called the resolution of X. Homologies are basically X. And it's called a cyclic resolution if the objects themselves are cyclic, so which we have. So here are two kinds of cohomologies. Yes, when we talk about the derived functors of F, we think about them as cohomology, and the Wurzel sign was shown by in a minute. And when you talk about actual complexes, you can talk about usual cohomology. So not to confuse between them. So these are just usual cohomologies of the complex, but nothing to do with them. But the fact that they're cyclic has to do with it. So what you do now? Now you just apply functor F. And then you complete the cohomologies of this complex. So it's rather easy to see. So maybe exercise 1. The first cohomology, the cohomology here, is just equal to f of x, which is compatible with the fact that the zero derived of f of x. And then exercise star says that all the other cohomologies have to coincide with the derived functor of f, assuming it satisfies this axiom. So just without knowing what is the derived functor, just by knowing the axiom of long direct sequence and the assumption, not really the axiom of enough cyclic objects, you can compute the cohomologies using a cyclic derivation. The derived functor, sorry, using a cyclic derivation.
And how?
How you compute? You
Yes.
take the cyclic resolution,
Yeah.
which you know has to exist because there are enough cyclic objects. You erase X, so this is the actual resolution, you apply functor F, and you compute the cohomology.
So the I cohomology will be Ri. X of X.
No, the cohomology of this complex will be
Yes,
the kernel, no, not R, no. No, yeah, the I cohomology will be as here. Ri f of X will be equal to the I cohomologies of this complex. Okay, here you need to know where we put the zero, so we want to put the zero here.
Okay.
This cohomology, the cohomology, this object is just the kernel of this map. It's the zero cohomology because just f of x. This is an easy exercise. The next exercise is harder. To show it for R1, it's already much harder. But somehow I gave you two algorithms to compute. One was like inductive, and one is like in one stage. You just need to show that they be the same. So one could think that maybe we get here not only a uniqueness proof, but also existence proof because we have an algorithm. But the two problems. One is the usual problem. When you have an algorithm to compute something, it doesn't prove that you have existence, just prove uniqueness. Because if the algorithm depends on choices, and it depends on many choices, you can get different answers. And you need to, in any case, you need to show that the result of the algorithm satisfies the answer. But here there is another problem. This algorithm is not real. You need somehow a priori to know what are the cyclic objects.
Yes.
So it's good as an algorithm once you somehow prove the existence in different way and compute and prove a specificity of many objects in different way, and then you can use it as an algorithm for compute. But it cannot be the first stage. It's like a posterior of adoption, and we will come back to it soon.
Well, also it's not just that you have to assume that you have a cyclic object. You sort of choose them, right?
The algorithm depends on the choice, but the result will not depend on the choice. If we know that the functor exists, then the result can depend on the choice. So whether it's proof of existence, no, you have to.
No.
Okay, you have to prove
But
that
maybe there are different choices.
different choices of what objects are cyclic. In fact, you are right. Yes, you are right. It did not. You're right. It did not say that. I didn't prove uniqueness if you just know that there are enough a cyclic object. I'm pretty sure it is correct. So if there are enough cyclic, so if you have a functor, a sequence of functors that satisfies these two conditions, then this uniquely defines a sequence. I did not prove it correct. But okay, maybe we'll see why it's their opinions and maybe. So now what about, so I want to talk about injective and projective objects.
Again, you say if we have enough assignment object, but it also depends on our eyes. Or do you mean just
Suppose we
object?
fix Ri that satisfies these two conditions. Have regular sequence and have an abstract object with respect to each other.
Okay.
And then I claim that this defines uniquely the sequence of Ri of f. But if I did not really put, I just give a recipe out to compute it, but the recipe right depends on who else that I. Okay, so now what is project? So acyclic objects are objects that thinks that the functor exists. So what are projective and injective objects? Those are objects that thinks that the home functor exists. I will explain what I mean. And the good thing about them is that they in fact think that any functor exists. Of course, each of them have its own side. So let's start with injective. Injective object is an object I have condition. I is injective if the functor goes to home xi is now notice that this functor is the contravariant, and this functor is always at z from one side. This functor is always at z from one side. I don't remember what side. And if it is exact, actually exact, then I say that I is inject. Okay, what does it actually mean? We have a method. I to x, which is 1 to 1. One of them. And we can continue it. Then x is 1 with I. And now let's apply this functor home to I. What do we get here? And I x to I. Okay, what's the good thing about and I that you have your identity, and you can consider its image here. This will be a map here. And now the fact that this goes to this map A means that this is basically a splitting of the sequence. So it's a projection to here. So if you go from I to X and back, you get identical. So what does it mean? It means that the kernel of A is isomorphic to X modulo I. So it means this just look like a short exact sequence, but in fact it's not a sequence at all. It's just a direct sum decomposition. Very direct.
Okay, so you're saying
I say that if I is injective, that any short exact sequence starting with I is in fact a direct sum decomposition. It's a more to short exact sequence. So lemma exercise and vacuum imply in fact equivalent and the style is dynamic. So what does it mean? It means, so this is direct standard composition. So any functor, any say additive functor, have to commute with that and direct sum. So when you say left exact, right exact, will always mean additive functor. So any functor will be exact in this sequence. So any functor which will be applied to such a sequence, yeah, have to be exact. So it means that I have to be a cyclic with respect to any functor which is left exact set. And now the funny thing is that here we talked about functor on X. This functor is not left exact, it's even contravariant, so it's not really clear what between left exact. But anyhow, it's not like the direction. But if we consider the functor, the same functor, but now I maps to X, right? Now X is fixed and I can be variable. So this functor is left exact. This functor is covariant, functor, and it is left exact. And I is a cyclic with respect to this functor, because cyclic with respect to any. And a posteriori, when we will have notion of the right functor and the right functor of O, then one can prove the following theorem. I will not prove now.
Why is I cyclic?
So I is a cyclic with respect to you need to have theory of the right functors for to talk about it. But once we can talk about it, maybe I didn't explain it yet. So yeah, I would explain it. So, but I at least want to be a cyclic with respect to any exact functor, because any such sequence goes to exact sequence. So there is no need in putting here anything. Now you can say maybe there is no need, but maybe there's still something there. Yes?
Okay.
So we don't know who are the right functors. So it might be that you have the right functor here, but this map is 0. So yes, the sequence goes to the exact sequence, but the object is not a cyclic. So you're right, we have to be more careful. We have to be more careful. Now I want to actually prove it. I'm a cyclic with respect to any left exact functor, assuming you have nice theory of the right. So if I mean any injective object. So we have injective object and say it is not a cyclic, or never mind, cyclic or not, it can be embedded into an acyclic object I bar.
That's our assumption.
That's our assumption with the order. And then, this embedding is a direct sum decomposition. And I didn't say, of course, but Ri of f, I want them to be additive functions. So Ri of, so it means that I prime equal to I plus some sum. So Ri of f I prime equal to Ri of f I of I plus some I. Yeah, but this is 0. This is the sum. Doesn't.
Oh, okay.
So injective objects have to be acyclic with respect to any reasonable theory of driving. And now we have a theorem which is correct, but at this point it's not even very formulated. Formulated that I is injective if and only if I is acyclic with respect to the functor y goes on y and if maybe if and only if for any C outside those spaces. And so now we have like 3 ways to think about injectivity. One way is that this functor is exact. So any object X is acyclic with respect to this functor. What can you say? Just this functor is exact. Another is to say injective mean like kind of universally acyclic with respect to any functor. And the cell means that acyclic with respect to some very specific chemical functor. And before we need to say somehow the system of the right functor for the functor OM, and it is correct. And now you can say, so now if you particularly have enough injective objects, so enough means that any object can be embedded into an injective object, then you can derive any functor or any left functor. Because you can declare, you know, a posteriori that they have to be acyclic, so you will declare them to be acyclic, and then you use the formula declared before with injective relationship. So if you have enough injective objects, which is not very common, then you're done. So what the reason that we want it to be more flexible is sometimes there are no. So now, so of course everything that I say from left, I can say from the right, but injective object. So injective object, when you reverse the order, the right analog is projective. And so now let's do some examples. What are projective objects in some situations? So maybe, so there's some additive abelian categories like vector spaces. When these are meaningless questions. Vector spaces, these questions are meaningless, but everything is injective, everything is projective, because every short-direct sequence is direct condition, so nothing to worry. So the first, maybe non-trivial example is modules over an arch. So what are the injective objects in the figure of modules over an arch? Or what are the projective objects? What the injective is how?
Our projective objects.
So okay, how injective objects? Okay, I can say the same words, but form just put it first. But maybe here it's better to finish. And each time you have an embedding, you have a projection on the side. So we can do the same with injective. Each time you have an onto map projection. This, you have a section of this. So do you know? No, not a big couple. What eats the P. Do you know a situation that each time you have a projection, you have a section? So how you would define a section? You can take element here, another element, but then at some point you might have some problems. Exactly. You can always try to generators and try to use them, but there are relations, so they might cause problems, but no relations, no problem. So free modules are always projected. And in general exercise, P is projective if and only if P is direct. Amen. Well, sometimes it means it's free, for example, there is very hard theorem, Queen system theorems that say that over the ring of polynomial hidden variables, and that projective set we are for one level.
So could you repeat that? So
the projective is equivalent to being direct sum.
Yeah.
And Queen says that in case of ring of polynomial hidden variables, projective and free are just the same.
Okay.
One variable is exercise, follow from the fact that it's the idea. You have to be careful if you're doing anything to generate stuff that I think is too easy. In fact, I think this theorem is only for finite generated. Then. So let's talk about finite generated. So for one variable is easy, but for two variables, and it's not important in general. No, it's hard. So this is projective. So, so what about injective? So let's not do in general, but what is injective abelian group? And so you can guess it in vector spaces, they are only injective. So you need a abelian group that behaves something like vectors. And this is called divisible abelian group. Any element can be divided by a group. Now, and if you exercise this star, abelian group is injective, you can leave, we could complete this. Not very hard to explain, but not straightforward. Maybe straightforward, but not. So there are enough injectable. So first of all, here you see that there are enough objects because you can map any object onto for any model you can map a free model onto actually generics. And here you see that there are enough injective objects because any abelian group you can just it's not divisible, so you add whatever you want to divide. But then but in general, so divisible doesn't mean that the division operation is unique. Yes, if you have finite group, you can group for order 5. You cannot uniquely divide by 5 because 0/5 is 0, but it's also 1. It's also by generic. But you can divide by 5. No, you can divide 5 any element, but 0 you can divide 5, so you can add 1/5. So your group is say Z modulo 5, you can add 1/5, now you can divide by 5. By any other prime number you can divide by. But it's not enough, you want to divide by 25, so you add 1 button, etc. So we get this union abelian groups, basically some rational numbers modulo 5. This it's not fine to generate the abelian group, but it's an abelian group, so we can. And here maybe you see the first problem. So the category of finely generated abelian group does not have enough function. Well, I reject all things. Well, I don't score basically. Basically, no, finely generated abelian. But the category of abelian groups have enough. So you can do theory of the right functors for abelian group. And in fact, you can do theory of the right functor for modules over any algebra. But you need to talk about infinite models. But the thing is that a posteriori, all the derived functors, at least for many functors, including the functor home, will be finitely generated. So you can also do theory for finitely generated options. But you somehow need to get out from this category in order to define it if you work with this test. Okay, so what are alternatives you have for defining derived functors? So there is this idea of F-adapted family. Suppose you don't have enough injective objects, so you want to define derived functors using a cyclic object. But there are no cyclic objects because you didn't define the derived functor. So instead you have this notion of F-adapted family.
What?
F-adapted family. So what is F-adapted family of objects? Definition X in C is or F that if one there are enough of it. F adapted this ID is
F is a functor.
it's a functor from C to D. Left it at equal to y for any y in C, but this is X and embedding y. Enough of them to make the solutions. 2, f max any, I think, finite, but not sure you have to need exact sequence. We object x, but not short exact sequence, can be large. So here you see you cannot really ask it to map only short exact sequence to short exact sequence. A posteriori I wanted that that family will consist of a single function. So you see that the posteriori said
Wait, but I thought that the cyclic object should be the first term. Or it's not actually.
no, okay, this is the problem here. So you see that you cannot, if you just ask here that short exact sequence will go to short exact sequence, it means that you can take any object whose first derived functor equal to 0. And this is not enough to do something. Then all this will by itself. We need to continue to pay action. So if you have an object whose first derived functor is 0, it doesn't mean that it's cyclic. Although it kind of means it in the beginning. If you just take a short exact sequence with this object at the beginning, then it maps to short exact sequence. But this is still not enough. So this is why I need these two axioms. Yeah, because you remember when we say we have inductive procedure to compute the right functors, we use the fact that all the answers are 0, because then we can connect with it.
No, but I mean, if you have what will be a right functor, and you take x to, you say the x consists of a cyclic object.
Yes, then this is adaptive term.
But
A posteriori, an example of adaptive family, and this fact the only example of adaptive family is family which is large enough that satisfy 1 and consists of a cyclic object. But this is not the definition of adaptive family because they can define the cyclic object before the derived function. So this is bootstrapping away how to define, how to know who is the cyclic before we know what is the cyclic. This is family, and the theorem if exist adapted family, then it is unique theory of with unique this unique sequence of functors that satisfies these two actions that we like. Vanish or have exact sequence and vanish on some large family. A priori doesn't have to be the same family, but of course, a posteriori, once the family is adapted, then these objects are well. Yes. So this is a nice criterion to derive functors. Not always work, but in many cases you have this criterion, and then you have nice theorem. There are other categories which you do have nice theorem functors without this criterion.
example.
So the best example is home. Any category home. You consider home a functor with the variables. Any category, and this functor have, so you can fix one of the variables from left and one. In one case it's contravariant, in another case it's covariant, in one case it's left exact, so the right exact will be defined correctly that it's contravariant, whatever. But when you derive it, and so you can derive both of them and get what's called X functors. The derivatives are the same, like in calculus, the first argument and the second argument are the same. I know it's not any kind of calculus, but calculus we have a result more over there. Mixed derivative, just one derivative are the same, and they call X, and you always have this nice theory. I didn't say formally what it means because you don't have enough cyclic objects. But we always have one. And for example, for finite generated Boolean groups, you don't have enough cyclic objective, enough common cyclic object for generalize.
But you do for
X.
right?
What?
But you do for right?
You do have the right hand of home. Now you can cheat, you can just use to derive the home or make the other one. The general way to derive home, and then we'll try to explain what does it even mean in the next hour. 15 minutes break.
Okay.
Oh.
Interesting.
So this theorem, I of course don't claim that I proved this theorem because I kind of gave an idea how to do it. You use this family as a candidate for acyclic objects, and then you use them for cyclic resolutions. But of course, there's lots of things to prove here. What you get is actually not dependent on choices and some first conditions, so uniquely defined, etc. But this is cool. And now let's go to an example of where you do not have injective object, but you do have adaptive system. This is probably one of the most important examples of the functors, the functor of global functions. So we have logical state X. One. That will take one. Let's take this one. You have shift on X, and you have and you have a sheaf of a billion books, and you have a billion. But let's even take sheaf of finely generated a billion books. Yeah. So we know that this category has not enough acyclic object because it doesn't have enough injective object, because even if X is a point, it doesn't have injective object. So, but if X is a point, then this is not a problem because this functor is the exact. Okay, so here is another example. If you have exact functor, then any family or any large enough family is up, you can just take all the objects, it's that family or this. And here is a notion of pledge. So definition is yeah, if restriction into so this is not a rare situation. This is where sheep usually don't expect the restriction to be odd. Sheaf of continuous functions, you cannot extend any continuous function from an open set to the entire set. You can stay constant shifts, and often you can extend if you have a restriction to a smaller open set, or sometimes you can extend. But if this smaller open set is not connected, or less connected with the original set, then you cannot extend the locally constant function to so you don't expect so what you can do but there are shifts exist. In fact, there are not. The idea is that for any shift, you can consider its stock at any point, and then you can have a very stupid shift. Any you consider just all sections, not continuous sections of all. This is a shift, and this is flat because when you consider all functions, all sections, then you can extend it. And you can embed your original shift into this shift because your shift is just continuous sections of this system. Shift. Here you take all sections. So continuous sections. So the shift is here. If the restriction don't.
No.
But how do I find conclusion? Say so start with shift F and make out of it a relation E over X. And then I consider the shift of all sections, not continuous, but all sections exist. And find G of F would be all G of F of U, so we call S of U. No, it's that to that we also apply F then apply E
U from S from U to what?
to E. So it's like if you would put your continuous sections, then you will exactly get reconstructed. And if you put any sections, then you don't reconstruct F. But you're embedding from F to the sheet. And this is sheet in thread. So there are enough threaded objects. And it's also easy to show that this is adapting gamma adapted. So again, let's say we start with whatever. B for gamma. This is not very good example because Freddy shifts are almost injected. For example, if you will not talk about it, so a shift injective, if and only if its stocks are injective object in the target category and it will flow. So if your target category of vector spaces, then Freddy shift is injective. So it's not very good example, but it already gives you something that you can work with. So sometimes injective Freddy's injectiveness is too strong, but you have Freddy shift. Now on the practical level, if you try to construct a Freddy solution, will be a cyclic resolution. You can't really, you can do it, but it's horrible. Yes, the first thing is already quite horrible. This is G of F. It's called Goodman resolution. Embed your shift to G of F, nice. But then you take the quotient of G of F by F, and then you do again Goodman embedding. If you start with G of F and you do Goodman embedding to G of F, you get something much larger. And this is something like this, but even more weird because it was there. Yes, because you have stocks of stocks, yes. The stocks of G of F are not the stocks of F. They're like huge things, yes. Families of sections in the neighborhood of F, but the sections can be completely based. And so the Goodman resolution is going to be infinite and it's going to be crazy. But it still exists. You can still compute. Well, it is defined homology. And then the other families of the other gamma adapted family looks better. So let me give another example of computation of homologies. Okay, so one of the main most interesting things you can do with the right functor is compute homologies of this. The right functor of gamma when you plug into it the constant shift. So we start with constant shift left, let's say on S1, and we want to compute its homology. So we know that we can find the resolution and then apply gamma, but the resolution has to be assigned. But it doesn't have to be flat. So what other resolutions there are? So here is a nice example, which you in fact already discussed. The constant shift is a subshift of infinity S1. And constant function is special case of sinus. And here we have the differential, the derivative. And this is an onto map of inversion bracket. You remember we talked about the fact that this is an onto map of shifts. It's not onto map of vector spaces, so on the level of local section. Not onto map per shift, but we know shift. And this is a shorted by sequence of shift. Now I claim without proving that these are gamma cyclic options. We somehow one has to prove it. Let's forget about it for the discussion. This is the same object, yes. So we find the cyclic object. Okay. So we have a cyclic resolution. We can erase this and then apply gamma and then get it from one. So what we have now we'll get C infinity of F1 B C infinity of F1 implied global section. this is not known to map. So this is still a complex, but this is not one-to-one, and this is not one-to-one. But it's a kernel and kernel. These are the two homologies. The zero homologies, which is a homology with each other kernel, functions. Okay, not very surprising, the global section, just see. Wow, but here we get something surprising. Here we get the one-dimensional space. And this in fact works for any smooth manifold. So for any smooth manifold, you can use similar trick to construct a resolution of the constant shift and take its global section, and then you get a sequence of vector space, which is by definition called, or by one definition, called the homology of this topology of this movement. So maybe you know what's this, when you know the sequence, you familiar with the RAM complex. So this is the RAM complex. But usually when you talk about the RAM complex, you're not talking about complex of shifts, yes? You're talking about complex of vector space. You have differential forms, global differential form, and you have differential between them. But differential form is something we define locally. For any open set, you can talk about differential forms on this open set. And then you have the differential between differential forms as a map between shifts. It's not map of shift of modules, so the whole structure of modules over the shift of smooth functions, because you can multiply for by function, but it's differential for one or more with the vector is not, but still. And shift vector spaces, you have this complex. And this complex is exact sequence almost everywhere, or except that in the place here. Why? Because so the differential is not onto, or it's not onto the kernel. It's not rooted at any closed form in that. But locally it is true. Locally, if you have closed forms defining some open small neighborhood point, you can integrate. You can find it's also set. So the differential of the other thing. So you got, and so, of course this works except of the place as a zeroth place. When you start with smooth function, closed form will be like constant smooth function, and constant and exact will be zero smooth function. So it's not the same, but the zero homology is just a constant, in fact, locally constant functions. So it's a constant shift. So the Rad complex, when you consider the complex of shifts, it gives you a resolution of the constant shift. And when you take global sections, you get and the homologies of the global Rad complex. And this is by definition the homologies of your topological space. All. It's a problem. Definition if x is 9 A image x or maybe not with position to any Abelian group. Constant shape is very simple Abelian group. And this can serve as a definition. You probably know other definitions of homologies.
What is A?
A is a Abelian group.
What is A?
Constant shift with values of the local function. And so this is not exactly equivalent to other definitions, so this is why I put the word nice here. So for nice topological space, it is equivalent to other definitions. And for not nice, it's not equivalent, but it's not clear who is better. Because for example, if you want H0 to be one-dimensional, you usually want your space to be connected. It should be equivalent. H0 is one-dimensional, if you only have the space connected. But formally speaking, it's not equivalent. Yes, if you define singular homologies, then H0 is one-dimensional if and only if and your space is custom. And if you consider this definition. So H0 is just global sections of the constant shift, which just mean locally constant functions. So when it is one-dimensional, if and only if the space is topologically connected. So what is better, topological connectivity or fast connectivity? So for weird topological space, I would say that okay, we don't have to know anything about how, so why they have fast connected. So somehow this definition is more topological, it's less, it has less to do with how. It's maybe work better for general topological space. On the other hand, you can say you don't do cohomology when your space is weird. So let's talk about say CW complexes. So for CW complexes, this definition is equivalent to any other definition. Homology. And one way to see it is basically to say that the other definition that you know, it's also something like this. You also apply a cyclic resolution to your topological space. So formally, it doesn't really work. And there is some problems there. You probably know this problem. So you took a course in algebraic topology. So you probably remember there was this Pythagoras theorem. And at some point, there was a problem there because you had a cycle and you want to somehow prove that this cycle comes from something on one open set and for another open set. But it's not true. It's like might be the angles are like all over the place. So you do many percentage subdivisions, and then you can that will separate. For this reason, so you can define a shift of like the singular shift, but it is not exactly a cycle. But it's still good enough to compute cohomology with it if you do it carefully. Yeah, I think you can define. No, you cannot. You cannot define it. No. No, you can. So I think we can define a shift, but it's not a cyclic, but we can compute cohomology with it. So basically, if you want to prove the RAM theorem that says that the RAM cohomologies are isomorphic to the usual cohomologies, then you need to, so you show that the RAM cohomologies are the derived phantom compute with certain set resolution, and other cohomologies are computed just with other cyclic resolution, or another cyclic for communication. And this kind of can give you a posteriori reasoning why there are so many theories of cohomologies, because there are so many theories of cohomologies that are actually different, but also there are many theories which are the same, but you just use them in very different ways, because you always confuse them and the phantom in different. Okay. Now that's the second. So now I want to start to talk about the derived critique. And more modern way, still not really modern way to consider derived. And so the idea is that what we're doing now, each time when we compute things, we choose a resolution, apply the phantom, compute the homologies. We can choose another resolution, apply the phantom, compute the homologies. So each resolution gives completely two different complexes, but the homologies are the same. But the thing is, they're better than just the same. There's some reason why they're the same. So here's an example of reason why homologies of two complexes will be the same. Definition. That one. More B.
This is 5, and the other ones are sheet.
Nothing C in billion category A. Next. Let I be more in complexes in a billion category A. And phi is value isomorphism. If and only if phi is the U I don't know if we want on from so if we have multiple complexes, it's sends a kernel to the kernel, the image to the image, because we can use this branch of the complex, so it makes the cohomology to the cohomology. If it induces isomorphism, then it is then it is called the paradise. And the thing is that in all these cases, when we prove that things does not depend on choices, we didn't prove it, but we say it, choose different resolutions, and not in any case you get the same sequence of the functors. And in fact, to prove more. In fact, to prove is that we can construct quasi-isomorphism between these two components. With one asterisk. So sometimes you can construct the quasi-isomorphism to one direction, and sometimes you can construct it to the opposite direction. And then sometimes you cannot construct it at all, because we need to go through another order. Once go one direction, another go to another direction. And theoretically, maybe we have to do like very long zigzags. But the basic tool of proving that cohomologies are the same is quasi-isomorphism. So if we prove more, then we need to use this more. And this is the idea of the last category. We will say that we not only care about the sequence of cohomologies, we care about the complex themselves, but only up to item, quasi-item. And this is this new category, it's called the derived category of the abelian. So what is the derived category? Definition. Category. Learn. Okay. B. B. Fine. B of A. Right, and then I will explain. So we declare that all the quasi-isomorphism are isomorphism in this new category. So we localize by this category. And we discuss in this in general, there is this procedure of application of categories by self-morphism. And we can define this category with this procedure by universal properties in the two categories of categories. So we need to say what it means to be universal object there. I simply say something like this. And but anyhow, we also say that we can construct it, and the idea is kind of horrible. You each time you see such an error, you invert it, but then you need to add composition with this inverse error, so you have to add sometimes for expense. And this is if this is quasi-isomorphism, so you have new map, but this is not enough in general. You need to do it again and again and again. So this, and then you have to add this. And this is also not good enough because now you have many errors, but some of them should be equivalent, just consider the same error, because there are some stupid relations that could be different. And after you do all things, then you can say you localize better. So this is disaster, and it's very hard to work with it. So there is a workaround here. So you probably remember we talked about all condition.
Okay, this is called the derived.
Yes, the derived category defined like this, and maybe with one asterisk. It's called complexes, but I didn't say what complexes. All complexes. So first of all, they can go to the right and to the left, or the change in symbol. That changes the way you think about it. That. And but also it can be we sometimes want to consider the full diagonal category or complexes, but sometimes you want to consider complexes that are bounded from below, sometimes bounded from above, sometimes just bounded complexes on both sides. Sometimes you want to consider them bounded from below by actually zero, that started from a fixed coordinate, or just bounded somewhere below, and the same result. So there are million versions of the F category, but sometimes there are even more versions. For example, your abelian category is inside a larger category. They trying to generate the abelian group inside the category of all abelian. So you can consider complexes in the large categories whose cohomologies lies in the small category. This sometimes makes your life much easier because then you can find solutions to this larger category. So I gave one definition, but there are many versions. But the problem with all these versions is the fact that we need to localize. And this is not nice, so there is a third definition which is equivalent to this one, but make our life easier. So the idea is that we have a notion of homotopy of maps between chain complexes. And this is kind of weird because the notion of homotopy came from topology, but the idea is that you can mute it with like a bracelet. So the definition is like this. Definition. Okay, very good. So we have A1, A2, etc. B1, B2, etc. So you have a map between them. So what does it mean to have homotopy? Homotopy is not an usual map like this. It's a map that goes like this, backwards. And it's called homotopy if I think the sum that plus that. So what is it? It's called homotopy to zero. So your original map is set to be homotopy to zero. There exists an homotopy such that when you do that plus that, you get your original. I think it's plus and not minus. And so it looks a bit weird. And the idea is that if you take, for example, chain singular complexes in topological spaces, and you have two maps between the topological spaces, then each map defines a map between the singular complexes, and homotopy between the maps define homotopy between these maps between the singular complexes. What does it mean homotopy between two maps? It means just homotopy of the difference to see. And exercise if f is on so zero, then f in a euro 0.4. So, and this leads you to the notion of homotopical equivalence. So two maps are said to be homotopically equivalent. No. Two objects, two complexes are said to be homotopically equivalent. Like in homotopy theory, if you have map for one direction, map to another direction, such that the composition will be homotopic to identity. What does mean homotopic to identity? When you take a composition and subtract identity, you get something which is homotopic to zero. And the homotopical equivalence is always quasi-identity, but not the other way around. And indeed, when we take all this resolution, or when we try to define homologies using resolutions, we sometimes can prove that the homologies are the same because, or the derived functors are the same because the two complexes that you constructed are actually homotopically equivalent, but sometimes not. They always will be kind of quasi-isomorphic, but sometimes they will not be homotopically. But you can define the homotopical category of complexes. So the homotopical category of complexes are category where the objects are complexes and maps are maps up to homotopies. So the abelian group of maps is the abelian group of the original abelian group of map complexes. Modulo is the subgroup defined by maps which are not open to zero. And once you do this, you have a way to make your life easier. Instead of localizing C of A, so we define the category definition K of A, or object of K of A equal to object C of A, and more inside K of A is equal to more inside C of A modulo null.
What? That's a definition.
Definition of K of A, so the objects are a set called the homotopy figure. Homotopy figure of complex. And alternative definition of the right category, very similar, but we first take the homotopy category, which makes sense because you see that there is something to prove here, but the map between C of A, the phantom between C of A to D of A has to factor through K of A because all the I don't do it on the spot, but I think this equality is rather weak. But the thing is that this category is much, or this way to localize category is much nicer. It does satisfy the OR condition. So you don't, it does satisfy the OR condition. So, I don't know, it's written like this. So we discussed it before, so it's coming from algebra when you talk about, so when you do just localization of non-commutative algebra, you see that you cannot really localize in the usual way. If you just say that you want to consider fractions like A and B, it doesn't really work because what does this fraction mean? It might mean B inverse A, it might mean A B inverse. You can say, okay, let's consider such fractions, but then you don't know how to multiply them. So when you localize algebra by some non-commutative algebra by a subset, you need to, or non-commutative group even, and not group, same group. By a subset, you need to add the very, very long groups. But if any fraction of this type can be rewritten as a fraction of this type, maybe with different numerator and denominator, then everything is much easier. Then you don't need to consider all that. And here in categories, the way to write it looks like this. So each time you have a span like this, which going the opposite way, instead of going normal map is just quasi-isomorphism, inverse quasi-isomorphism, you go into the quasi-isomorphism then actual map. You can replace it by a map like this. So it means that you can find a couple of this, such as these diagrams can be. And then it means that you don't really need to consider such guys because you can replace them, and then your category will become much simpler. Objects are morphism between categories just spans, just most of them, and then opposite of product. Now, of course, you have to do it up to some good installation and have to find some way to compose them, but you have it. So this is the notion of the derived category. And this is unlike derived functors when we say we have some condition, etc. For any abelian category, you can define it right. And the idea is that you consider complexes, you think about it as a collection of complexes up to quadrides. So instead of defining derived functors, the sequence of functors, you just need to define one functor to the derived category of the second category. So let's see. So, so you have two categories for A and B. So you have the derived category of B. So what does it mean to define the derived sequence of derived factors? So generally just sequence of factors from A to B. But we say that each time we actually do it, we do something more. We write some complex in B, and this complex is not really well defined, but it is well defined up to value item. So we expect to have a functor like this. And now we need to say what we want from this functor. So the first thing that we notice that once we expect to have a functor like this, we in fact want to expect even more. We want to have a functor like this. So such functor, of course, will give us. You can just compose the functor. Here, this functor is not a composition. Yes, if you take composition, you get something stupid. Just any object in A, it's also object in B, and then it's also so gives you an object in B, and any object in B is object in the derived category, but it's a stupid object, just represented by a complex that lives in one place. So we don't want this composition. But here you can do this composition, and how you would define the functor from here to here. So each time you add the object, you can do the injective resolution or some cyclic resolution of this object, and then you can compute things. What happens if you have a complex of instead of an object, a complex? So the idea is that if you have enough cyclic objects, that any object can be replaced by a complex which have the same cohomology. What does it mean to have the same cohomology? You have object, we can see it as a complex like this, which has three components. But you also reconstructed this complex by 1, by 0, 1. And of course we have this map. Yes. Of course of this map which are 0. This map is quasi-isomorphism. Maps K, X to exactly to the kernel of this map, so the first homology, and all the others just 0 goes to 0.
So the map from B to direct category takes X to this.
Not exactly. We take X, first of all, we replace it by this complex, and then we apply our functor object Y. And then, yes, then we say, we wanted to say we take the cohomology, but we don't say it. We just say, consider this complex, but as an object with derived category, so we consider it only up to quasi-isomer. And now, a map from
Sorry. Here we have some sort of fixed functor.
maybe wait, no, because it got confused because you said I think they understand. So we start with an object X, we find a cyclic resolution. Now I say that this cyclic resolution, we can think about it differently. We can think about it as a complex of a cyclic object, which is quasi-isomorphic to this complex. And more generally, we can start with any complex here. It's slightly harder, but any complex, say, starting with 0, x1, x2, etc. We can find a cyclic complex of a cyclic object, etc., and maps like this, such that this is quasi-isomorphic. You can prove it, it's harder than to prove that a single object has a resolution, but this is called resolution of. So the idea is that if we have enough injective object or enough whatever, we can start with any object here, any complex, replace it by a cyclic object, and then plug it into the functor, object by object, and then get the object. So before I define what to derive functor, I give a way how to construct it. If I have enough whatever, I can construct a functor like this. At this point, I don't really prove that it's independent of choices, etc. But even if it's a functor, I'll just give a recipe how to compute it. So what did you want to ask? Now it involves. This place. Yes. So I start with 2 billion units, and assume that there are enough objective objects. And now I claim that I can construct a functor like this. How do I do it? I start with an object here, which is a complex. But I don't say anything, just keep it a complex. I replace it with a cyclic resolution. So a complex that consists of injective or whatever object, and that quasi-isomorphic to the original one. And then I send this one to here, just applying my functor on the objects. Okay. Here is something that I forbidden to say. I can't say take your complex and apply a functor on the object on the complex and you get a functor of this. Because this will not respect quasi-isomorphic. I can have two things which are quasi-isomorphic, but after applying the functors, they are not quasi-isomorphic. For example, I can have 0 and exact sequence. They're quasi-isomorphic, but after applying the functor, the exact sequence stop being exact. So not quasi-isomorphic.
Yes.
But if I only apply my functors to complexes that consist of, say, injective objects, then it cannot happen. Then if I have two complexes consisting of injective objects, if they are quasi-isomorphic, then my functor has to be. In fact, then they are homotopic equivalence, and then my functor has to be. Yeah, assume before it, and say left it. So this is the idea, the procedure that gives you derived functors between, not just functors between series of functors between different categories, but functors between the derived category of A and the derived category. So I defined the procedure, but now I want to actually define what by properties or what we're actually doing. And the idea is that we want, so we don't want this diagram to be commutative, but we do want a map from one composition to another composition. In this case, this direction is and we want it to be universal out of basically all options that we have. So let's say slightly differently. So here we can take just the actual composition, which is that yes, we can start with object A, send it to B, and consider is as an object in BB. And then here we want isomorphism to the composition. Sorry, not isomorphism, morphism. Yeah, to the composition. And we want it to be universal, and this is picture that you already saw. So this is a Khan extension, or the right Khan extension. So here's a way to define the right functor. You take this composition, and then you take, say, the right Khan extension, and then you get the rest. Of course, if you want the right from the left, you have to take all with the left. And this not only gives you uniqueness, because that's something defined, it also almost gives you existence, because in many cases you know how to define Khan extensions. And you see that you don't really need a lot. You don't need enough projective and injective, acyclic or whatever. You could just take limit over everything. This is the idea of Khan extension. So Khan extension is just call extension. It's not an extension. It's not that you extend this functor from here to here. You get a new functor which is new on A. This is the right functor on A. This is factor of the input. And so, but the Khan extension usually works. And so it's okay. First of all, it usually exists, and second, it usually gives you what I would say the right notion of the right functor. So you say, what's the right notion? This is the notion why we need another one, because today we have another one, which is also Khan extension, but in a different setting. And a priori they don't have to coincide. But in most natural cases it does.
If you're saying that this gives us the direct one.
Yes. Start with functor from A to B. You do this composition, you take the Khan extension, you get a functor from here to here. In particular, you get a functor from A to DB. You can take its homologies. So in DB, you have series of functors that from DB to B. So this This composition, is a like that. But in fact, you should not do it anymore. You should say just that the right functor is the result of this. Is the result of this procedure. There is just one right functor from dA to D. And basically, this picture, which is at least on the philosophical level much simpler than everything you saw before, just this functor kind of extension, you have that. Generalize everything we had before and more. It's still not the final word, so it still not really gives you the correct answer sometimes, but usually. Questions? Okay.
כן, 12:15. איי.
אני הולכת להחליט. יש לנו עוד 10 דקות.
אפשר לקצר את ההפסקה.
מה?
אם את רוצה לקצר את ההפסקה,
אני אומרת שאני רוצה להחליט.
כן, אם זה יכול להיות יותר מדי. לא צריך כסף בשביל החליטי?
מה?
לא צריך כסף בשביל החליטי, זה מפתח.
כן. יואן.
Okay. So we had all this long story before, and here we kind of have a short definition. But of course, some things have to be proven. For example, why do we have short exact sequence, a long exact sequence? For this bounded map, bounded sequence. A priori, if we have some functor from derived category to derived category, if we plug in objects in A, we get sequence of functors, but a priori we don't have it. And the idea is that this functor is not an arbitrary functor, because these categories are not arbitrary categories. They have some additional structure that was called triangulated category. It's technical, it's long, and it's probably kind of unbroken, so it's not really work very well. And this is why one of the reasons why this theory is today kind of outdated. But what it does give you is that if you start with an object in A, consider an object here, and if your functor preserves this triangulated structure, this additional structure, so it's called triangulated functor, or sometimes just exact functor. Here it's not a binary category, so we cannot talk about being exact in the usual case sense, but there is some other notion of exactness. So if this functor is exact, then you will get this long exact sequence. So I can say shortly what does it mean triangulated category. Okay. So it means that you have some collection. So first of all, you have here a translation functor. So there's some complexes, you can translate it from the left to the right. And then you have collections of objects here that call exact triangles. So not objects, so triangles. What are triangles? You have object here X, you have Y, you have Z, and you have this. So such thing you can call a triangle. So X to Y, Z. Object here? No, obvious. Yeah. So exact a triangle, say it's a sequence like this, which is kind of infinite, because once you do it, you can continue it infinity, but T is fine. The like things so different like this. So here you have an actual morphism, and here you have morphism to the shift X, to the shift of the first. You have some collection of triangles that you call exact triangles. And you want, and this collection has to satisfy some axioms. And you want that exact triangle here will be mapped to the triangle here. And if you start with exact sequence in A and consider it as a sequence here, then the triangulated structure is built in a way that this is an exact triangle here. So you get here an exact triangle. And if you have exact triangle and you consider it cohomologies, you can see from here that you have kind of a long exact sequence, at least you have long sequence, maybe it's not exact, but the fact is that it's exact. Because this is basically the triangulated structure. So maybe a better definition of the derived functor would be not just a universal extension like this, but universal extension like this, where this thing has to be triangulated. But the good news are, at least as far as I understand, and that you don't really need to impose it as another condition. Once it's universal, then it's automatic that it maps exact triangle to exact triangle. And this is the way you get from all this theory, abstract theory. Long sequence. Okay, so this was kind of breakthrough because the idea of derived functors without this actual name existed kind of long ago. So first of all, formally so there was cohomologies of topological spaces, and there was group cohomologies. So group cohomologies are derived functor, or group cohomologies are derived functor of the functor of invariant. So if you have a group action of one, say a billion group on another group, non-abelian group acting on a billion group, you have G acting on A. So group cohomology is the derived functor of the functor of invariant. And group homologies are the derived functor of the functor of co-invariance. So coinvariance. You remember what coinvariance? So what is invariance? Invariant A of G is a sub-object of A, and which G acts stable. What the coinvariant is a quotient object of A, the large quotient object of A, on which G acts stable. How you define it? You take A and you kill all the things that you have to kill.
Okay.
So this is something exact, called left exact, this is right exact, or the other way around. And you take the right functor of this, you get cohomologies, and of this you get cohomologies. That's confusing. And so you have two cohomologies, these are both special cases of X and torts. What are X? X are the derived functor of the home functor, and you can derive the first coordinate, the second coordinate, and you get the same answer. And tor are the derived functor of tensor product functor, which are also here, of course, the tensor product is primitive, so we can derive it whatever we want. So this one also theory existed for in many special cases for a billion. And now but it was like hard work, and each time like a different resolution, etc. And Grothendieck basically unified all these theories and defined the notion of derived functors, first for the sequence of functors, and eventually the one we do. And functor between the derived categories, to find the derived category, and that's it. But for the beginning, it was kind of clear that this theory is not perfect. So I think one of the most one of the problems that you see with it is when you consider shifts over topological space. So you can consider shift over topological space, and then you consider the derived category. And in order to define a shift, so the category of shifts is also a shift. So in order to define a shift, it's enough to define a shift on each open set and isomorphism between the shifts on the intersection. Of course, this is not really enough because it's a triple intersection, you want things to be. And you can see that it will be the same for the derived category. And it's not. We can define objects in the derived category by gluing local down. In that book. And the reason that these things doesn't work that you hear quotient by equivalence relation. So maybe the most naive case for the derived category would be, let's define the category to be just a collection of all complexes up to infinity. And this is really wrong because it's not category. So in order to make our category, we say we don't quotient by equivalence relation. We reserve the same object, but we just add morphisms. But when we add morphisms, we see that we have to put equivalence relation on the collection of morphisms. Also, even if we just do the homotopy category, we put equivalence relation of a set of morphisms. And this is usually a bad idea because once you put equivalence relation, there is a reason why two things are equivalent. Here they're equivalent because there is homotopy. Here there was some other reason. And if you forget the reason and just say the things are equivalent, you lose information, and then you can glue things together, for example. Because it's not enough that there will be equivalent, the reasons also have to be compatible. And this probably was the main motivation to go into the world of infinity categories. So it looked a little bit weird because at the first glance you would think, okay, we don't need so much motivation. We have categories, we have sets, we have categories. We already saw that we had the notion of two categories. It's important to us, for example, when you do constructions with categories, you want to define localization of a category, cell quotient, or whatever. We want to do it in the collection of all categories. We want to be able to talk about universal objects there. So we need the notion of two categories. And we even saw that we have monoidal categories, which is great motivation for talking about two categories. Because two categories, just monoidal category. So monoidal category is two categories with a single object. That represents the endomorphism of this object. I'm going to be a category which is monoidal because we can take composition. Like monoid is category Very similar to the categories. So it looks very natural to go this way. But in math, when you want to define a new notion, you need a really good motivation, because first of all, because doing new math is hard work, so you want to have something more, some good reasons for it. But some people will say, no, I don't need good reason. If it's natural, it's clear that something that has to be done, let's do it. It is correct, but then how we know it is correct? You need some way to test your work. Yes, so if you prove the theorem, then it's easy way to test to prove the theorem. But if you're defining a new notion, okay, everybody can define a new notion. We don't want to be they are what? Obviously in English. It's liberal science, whatever how to call it. Social, no, social science, whatever. You want to be able to somehow say that this construction is good. The best way is to solve existing problems. And to solve existing problems, it's just generalize into higher category. At least for sometimes there was no step, too much such problems. But the derived functors are everywhere, because in algebra, and not only in algebra, once you leave the world of the bigger categories, you also want to do some, although it's not called homological, because this is called homological algebra. If you work non-bigger category, it's called homotopical algebra. Basically, the same theory can be extended to some extent for general categories. And homotopical algebra is more everywhere in algebra and sometimes outside algebra, because this non-exactness is something that you always feel. If the functor is not exact, you feel it, because some weird things happen. It's like the square root of z. Yes. You go around and you see that you got different numbers. Yes. And this is exactly this cycle that appears all over mathematics. And
What does
this is what I want to say.
Okay.
So we have this basically one example of trying to localize something, trying to, or even not to localize, just quotient by some equivalence relation. And we need to remember why we decided that two things are equivalent. And this knowledge why is basically a morphism between these two things. So a better way to think about the F category is categories objects are, or even the homotopic category. Objects are complexes. Morphisms are morphisms between complexes, not up to homotopy, just morphisms themselves. But two different morphisms might be homotopic. And then it means that we have kind of morphism between two morphisms, the homotopy itself. But also two homotopies can be homotopic, this also can be defined, etc. So suddenly we have all these infinite levels of equivalences.
Wait, can you explain again why two morphisms?
Two morphisms between complexes, you know what it means that they're homotopic.
Yes.
That there exists homotopy, but what does it mean exist? There are many different homotopies. You want to remember that.
Yes.
So you say they're not equivalent, they're different morphisms. They just have a morphism between them.
I see.
But then the homotopies also can be equivalent in some sense. There is also homotopies between homotopies. But don't say that they're equivalent. No, they're different homotopies. Just there is a homotopy between them. And then you continue up to infinity. And although it's at the beginning very hard technically, but at the end it solves lots of problems that people had with the life category, for example, the fact that you can do them. So there is a price, because now you need to show much more compatibility. You need to show that on each two intersections the things are isomorphic. But in triple intersections, you get two isomorphisms, they have to be the same, but there is no the same anymore. They have to be isomorphic. But then quadruple intersection, these isomorphisms have to be the same. There are several of them, but there are combinatorial ways to say all these things like in one line. And as far as I understand, this is the main motivation for what we have. And it's kind of reflect on all the theory, because what you see here that okay, derived category, you have complexes, great, you have morphisms, which of course not necessarily invertible. But when you have isomorphism, homotopy between morphisms, it's kind of two-sided thing. If you have P homotopy to C and C homotopy to Phi, they find they change. And the same with static theory. The same with the derived category. Here I talk about homotopy. So somehow all the this infinity structure that you have, if it's concentrated after the first level. Yes. So sorry, it's so after the first level, everything is inverted. So the terminology is kind of weird. So it depends who you ask, but some people that say infinity category, they don't really mean what is reasonable to call infinity category. So it's not even generalized the notion of two category. They mean something which is behaved like an usual category at the first level, so the objects, morphisms, but then all the other morphisms between morphisms, etc., they all have to be inverted. So it's kind of special case of infinity category, and more like cautious people will not call it just infinity category, they call it infinity one. Meaning you have infinite many levels of morphisms, but only the first level is allowed to be non-inverted. And so the word infinity category can mean like actual infinity category, but some people when say infinity category, they mean infinity one category. So when you want to be careful, you can say infinity one category, infinity n category, infinity category. But somehow these guys are the most, or this is the beginning were the most useful guys. Because these are the guys that allow you to localize when otherwise you cannot localize, allow you to add equivalence relation, for example, when you define the last category. And often this just calls infinity category, but these are like much more modern guys and harder to define. I think this is maybe still not really fixed. So this is okay, this is now more or less okay, and this is I'm not sure. So it's still.
People research the top one.
I don't. Maybe what I'm saying is not updated, but yes. So at least 15 years ago, yeah, I would say. Now I don't really. So again, most of the people will not research any of this. They will like in category theory, useful outside category theory. So there are some people that research category theory, but most of the people that dealing with categories they not research category theory. They just use, and usually they use the basic stuff. But in the last 2 decades, the theory of infinity categories become much more useful. And so it's not basic stuff anymore, but usually still this level. And as far as I see, the main reason, at least the original motivation was just to replace this hard-working notion of derived category with the correct one. And like the correct one give you here infinity category, but infinity just in this sense, infinity one category. We don't need non-local deep morphisms. And then basically the same picture works, and then it works like really very large generality, very clearly. Okay. So another topic that I wanted to overview is a topic of sites. It's like topology on categories. Maybe it's not really good name, it's not site, Gothic site, or Gothic topology. So Gothic site is a category equipped with topology. But when I said category equipped with topology, it's maybe not very good to think about it. It's not that the collection of objects with topological space, but like if you start with topological space, there is a category of this topological space, it's topology. So site is a category that equipped with some additional data that make it similar to top X, to that topology of X of a single object. So I will say the definition. So the idea is that you can define. So we define a topological space a notion of sheaf and a notion of class sheaf. And arbitrary category, we also have a notion of class sheaf. But it's a simple notion. So we want to define the notion of sheaf, so for this we need the notion of couple. Couple. So definition and developing the topology on people. E for selection of collections Oh, sorry. I will not define the actual notion of Gaussian topology because it's very polygon. The notion of Gaussian topology is almost as useful. I will talk about the difference in a moment, but basically almost as useful. So we need collections, UI controls. So there's one called so basically for each object in the category, we can say when such a collection, it's not a single map, but several maps, we call them covers.
I is an N
I know.
in some.
It might be very large cardinality, but often the time.
Covers.
Covers, so
Covers.
like this.
Yes.
This. Something. But reveal all those things. So we have a notion of what it means for collection of maps to be a cover, just a set of things that will solve covers. And of course have to touch something. One, stability, and the base chain. What it means? WI. X. Now, of course, they want the category to have copies of products.
Y and X objects in C.
Yeah. Y. Also, I can pull back. If I have a cover, I can pull it back to Y. I want it to stay covered. The idea is that if you cover a space X and then you restrict to subspace of it, it's still a cover. And now composition. So if we have UI, and here we have Vij X. So if we take all the things upstairs together, they cover the things down.
Yeah. You have this covers for OX.
Yeah, for all X, for any X in the category, I have a notion of what it means to be a cover. Several matches and together cover.
Okay.
And now if we cover X by several maps, and then each of them are covered by several other maps, then we want to have the total cover. Of composing also maps downstairs and get cover effects. So this is a requirement. With this new thing, will be also a cover. And the last axiom is your axiom. Well, isomorphism is a cover. And so this is not what we call a topology. The idea is that this is something that gives you enough information to define a topology, like basis for graph topology. But unlike basis, which is kind of not natural, this I think is natural enough for most applications. So you can just consider this a definition of a Gothic topology, and you will be. No, this has nothing to do directly with topology. I just say it's analogous situation. So from Gotham's point of view, he didn't call it topology, he called it a topology. And his point of view was that this is like a basis of a topology. So it's not topology by itself, but it defines something else that we actually call topology. And two different topologies can define the same topology. But any topology is defined by some topology. And unlike the situation with basis, when basis is kind of a natural thing, yes, you need to know what are the open sets. It's not enough to know what are the basis points. Here, it's more or less enough. So I live most of my life thinking that this is a Gothic topology, and most people.
So does this have a notion of an open set?
Not really. Instead of this notion, you have just a notion of open cover. So you can think about maps like this that are part of an open cover of a cover, that they're kind of open, but it's not really work. Yes, not very. So maybe the best analog of open set is also not really correct, but just morphism. And because when you find a Polish sheaf, So let's do the example of top X. So top X is a category of cosecant category. So what is the sites, the Grothendieck topology on these tokens? When we say that several morphisms exist in this category that cover a single, that maps to a single object, are covered. You know what to say when you say when they actually cover. What are morphisms? Just embedding of open sets. So if you have several open sets that cover the entire thing, some target sets, then you say that this is a cover. So this is your Grothendieck topology on this category. Very natural. And why we define this thing with covers? Because what do we need actually to define the notion of sheaf? Sheaf is something that gives for any open set a set. It's contravariant when you have restriction. When you have embedding of open set, you have restriction. But it also satisfies the sheaf axiom. Now, before the sheaf axiom is just presheaf, and you can define it for any category. It's just a contravariant function of a set. But now, if you have this notion of covers, you can define what is a sheaf on a site.
Yeah, what is the site?
Site is a category equipped with a Grothendieck topology. So a sheaf on a site is a presheaf on the site that satisfies the sheaf axiom with respect to the covers.
Okay.
And not only can you define the sheaf, you can basically repeat all the theory of sheaves, including cohomologies. Now, you don't have global sections anymore, but you have the forgetful functor from sheaf to presheaf. And this is like global section, but you just make section of each object. And this functor is not exact, because you have a notion of onto map and sheaves, which is depends on these covers. Yes, that you can always define the cover. So we don't really have to be open onto. We need to be onto after you define your cover. And then the derived functor of the forgetful functor of tuple sheaves are called the cohomologies of this sheaf. So you basically can repeat lots of theory that you have for topological spaces to sites. Not all of it, but lots. And why it was so important? I think the first and maybe the last example is algebraic geometry. No, not the last. The main example is algebraic geometry. In algebraic geometry, you have the risk topology, which is actual topology. You have open sets, you have covers. This topology does not reflect anything about the geometry of your set or orbit set. It reflects something. Let's say connectivity, for example. If it's connected at a topological space, then your variety is actually connected to a variety. Like say your C is connected to topological space. But if you even like most basic thing, whether it's compact, whether it's house there, so this topology never house there, always compact, or it's what's called quasi-compact and compact without house there. Although your variety is usually house there, yes, if you want to think about it, say the solutions of a C, it usually will be Hausdorff and usually will not be compact. It's not compact. So you can define with this topology the most basic things, and of course you can define pi1 or h2 or whatever. You can define h0 and pi0. Yes. This is the and there are many reasons for it, but probably the main reason is that you don't have the implicit function here. You have functions like squaring, say from C star to C star, and you don't have a square root, even not locally. Not locally in the root of the point. So you want to change, you want somehow to impose that the squaring will have a local section. There's a map. The map of the square, for example, will have a local. And how you know when to impose it? So there is a notion of a Tal map. This for smooth varieties is a very simple notion. Like the differential is like a Tal map for smooth varieties. A map between two smooth varieties with the Tal, the differential is like. And in differential topology, once your map is a Tal, you don't call it Tal map. You can find it at least. You have a local section. And in the risk topology, you don't want it. You don't have a local section. So you want to postulate these maps have a local section in some topology. And the idea is that you say that these maps, you can think about them as open subsets. They are not open subset, they're not subset, they're not one-to-one, but you think about them as an open subset, and then of course they have local section because on the set. And this is a way to define the étal site. So there are many versions, but let's take the simplest version. You fix an object X, and you consider the collection of all maps, étal maps from A to X. You get a category. The over category of X, so some subcategory of over. Yes. And it's a full subcategory of over category because it's 1, 2. You can consider any map like this, but since they're over X and each of the maps will pass, so the maps are étal. And this is a étal size, that's more étal size, never mind. So this is a category. And you can consider shifts in this category. You can consider the constant shift. Let's take not with values in C or in Z, let's take the constant shift with values in the abelian group, let's say C5. And then you can compute the homologies of this shift, like the derived functor of the global section functor. So we say we don't have global sections, but we do have progressive functor for shifts. But in this case, you do have global sections. And you just can consider the sections of X. You have terminal objects, so you can consider where the terminal object. And then you get actual non-trivial sequence of abelian groups, or in fact, let's say we can consider the effect of I5. So you get non-trivial sequence of vector spaces of I5. And this thing actually corresponds to the cohomology of X, say if X everything was defined over C. So this thing will be actually isomorphic to the cohomology of the singular cohomology of the complex point of your variety with coefficient in F1. So there is a completely algebraic way to reconstruct the cohomology of the complex variety defined by X and with coefficient in F1. And this was like the main application of the type topology. Now it doesn't work for non-finite fields, not direct. So if you start, we can do it with finite fields, you can do it with finite groups, finite abelian groups. If you plug in coefficient with Z, you get some notes instead of another word, something like that. And the trick is that okay, you can do it with coefficient with Z, but you can do it with coefficient with finite group. So you can take Z0 5, like 5, but you also can take Z0 25, and Z0 125, etc. And then when you take limit of all this picture, you can do things with coefficients with Z. And then if you want, you can Z5. You can extend the scalars to Q5. And so we can do things with coefficients in Q5. And Q5 is basically isomorphic to C, so we can do kind of complex homologies. You cannot really do homologies with coefficients in Q, but you can do like they have the same beta numbers, so kind of you can do it factorially. And if I said a 5, but if your characteristic is 5 and you try to do it over a 5, it's that idea, or at least you get something, maybe not that idea, maybe it's very interesting idea, but you get something very different. So usually you choose a characteristic which is different from your characteristic of the field. And since often the characteristic of the field called P, then this characteristic will be some different letters, so usually we choose K. And then it's called Elladic homologies. Your space, because they're kind of your variety, because there are more business coefficients. And this you can do with the null site, and you can do it, and there are other sites which are some equivalent to it, some are not. So you can change the collection of what maps are good enough for you to call them covers. Yes. So usually you don't want to consider cover with points as covers. It's okay that often it's okay that you to add to your cover some dead maps, but they will not make it a cover. So what you actually want to cover everything with some nice good maps like étal maps. So étal maps are okay, and there are some other nice topologies that people consider differentially biased. I don't think I saw a use of sites outside algebraic geometry, except of one exception, which is also not really outside algebraic geometry. There is a notion of restricted topology. Restricted topology is very similar to topology, but you don't ask an infinite union of open sets to be open, only finite union. And then you also can define the notion of shifts in respect to topology and gives homology, and big part of the theory of topology survive on the also when you talk about the space topology. And one way to see it is that state topology is a special case of site, but just you change the definition of cover, so you enforce that your cover has to be and then the Shiva axiom becomes much weaker, somehow weaker. You have to work only for open cover. All the way to do geometry in this way is kind of different because you choose only finite covers, and this can be used slightly outside algebraic geometry, at least depending on the financial geometry. So these are the sites, and they work very well with the notion of the categories, etc. Yeah, I think this is mostly what I want to say.
Yeah, I lost you.
Yeah, I can repeat it.
Huh?
I can repeat it, but maybe I will close the Zoom and then I can repeat it in Hebrew.